Hello friends, welcome back to the channel. In this channel, we try to solve the previous year's physics question papers of Neet undergraduate exam. This is also helpful for JEE Mains exams as they pertain to NCERT syllabus. This is solved in a very student-friendly manner so that you can understand and apply the concepts. We have included all types of questions appearing in the exams so that your preparation is complete. If you like the content, we urge you to like the videos. This motivates us to create more content and help you in your exam preparation. We also urge you to subscribe to the channel so that you are immediately informed of any content added to the channel. If you have any doubts, then please feel free to add in the comment section and we will revert to you at the earliest possible. So without much ado, let's get started. So friends, in the earlier video, we had posted some questions pertaining to electrostatics and capacitance. So in this video, we'll be solving those questions, but before we solve those questions, it will be worthwhile going through some vital concepts pertaining to electrostatics so that it will help you in solving these problems. Okay, so we will start with the concepts. In concepts, we first talk about the electric charge. Okay, there are some properties pertaining to electric charge. One is that first is that they are additive. So the total charge of a system, if there are n charges, the total charge will be just the sum of all the charges. So for example, if you have a system in which there are multiple charges, for example Q1, say Q2, Q3, etc., right? So the total charge is the total charge of the system. So for example, if these are the total charges, then the total charge will be the summation of all of them, right? So summation of Q1 plus Q2 plus Q3 plus Q4 plus and so on till Qn. Okay, so that will be the total charge. Okay, so that is what means by additive property. Second is the conservation property, right? So it means that the total charge of the isolated system, it will remain conserved. So if there are multiple charges in a system, then what will happen is that the system will actually can get transferred, the charges can get transferred from one entity to the other, but the total charge in the system will remain conserved. Okay, this isolated system remains conserved. Okay, so this is about the conservation. Third is the quantization. So it means that the charge will also always be in multiples of E, okay, where E is the charge of one electron and proton. So we always will talk of Q. So Q will always be any, right? It will not be half or 3/4 of E. It will always be in a multiples of the charge of one electron or a proton. Okay. The next is that now whenever there will be charge, so there will be an electrical field which will be created because of the charge. Okay, so how will that be, how will it show up? For example, imagine if that this is the electrical charge here plus Q, then this is electrical field, right, in which you'll see the electrical field is moving away from this, right? So it will be outwards from the positive charge, right? It will be outwards. Remember that this is outwards here. Okay, on the other hand, if it is a negative charge, then this will be inward. Okay, electrical field will be inward. Okay, so please remember this is very important. Okay, now what happens is that the moment we introduce a charge, right, then what happens, because the electrical field, there is a charge which is getting introduced in the system. So for example, if there is a Q here, okay, and because of electrical field, then any point here, for example, so there will be a certain charge here. Okay, it will not be neutral. Okay, depending on whether it is positive or negative, so there will be a electrostatic charge at any point away from the charge, right? So imagine a charge plus Q, which is being carried from A to B with zero acceleration. Okay, so work is being done. So imagine that if you are carrying a charge from which is the quantity of the charge is plus q, we are carrying from A to B, then because B is closer to another charge q, imagine that near B we have another charge which is plus q, right? So the moment I'm carrying a charge plus q towards this, so there has to be a repulsion force, because those are both are positive, right? So because of this repulsion force, it means there is be some work which has to be done to counter this repulsion force and bring this charge q towards A. Okay, right? So this, now imagine that we bring the charge and we station somewhere here, right? Correct. So this particular work, whatever we've done in bringing this charge plus q from infinity to this point, this will be saved as the potential energy. This will be saved as the potential energy. Okay. If the point from where it is brought as infinity instead of A, then assume that at infinity the potential energy is equal to 0. Okay. So the work done by an external force in bringing a unit positive charge, it is equal to the electrostatic potential at that point. Okay. So whatever work is being done by the external force in bringing a unit positive charge, that will be the electrostatic potential at that point. So delta U is the potential energy difference. It is equal to UB minus UA, and this is the work done in bringing that charge. Okay. If what we said is that if A is at infinity, then U at infinity will be 0. Then the delta U, which is the change in potential energy, which is equal to UB. Okay, the work done by the external force in bringing unit positive charge. So if you are bringing a unit positive charge from A to B, then this will be the change in the potential. Okay, this will change in the potential. Let's go to the next slide. So work done by the external force in bringing unit positive charge from A to B is equal to BB minus BA is equal to UB minus U by Q, because we are talking of the unit positive charge. Okay, unit positive charge. VB minus VA is the potential difference between A and B. One more important thing is that the work done on our test charge plus Q by the electrostatic field, okay, due to any given charge independent of path. So imagine that if there is an electric field here, we are carrying a charge, right, from this point to this point. So this is doesn't the charge is the path is not significant, right? Whether you take it to this path or whether you take it to this part or whether you take it to this path, the path is not at all significant, right? What it signifies is the final destination and the starting destination and the distance between them. That is what is important. Okay, the work done by external force, so what is the value of this? This is Q by, now we'll have to start remembering some formula, which is Q by 4 pi epsilon R. The work done in bringing a charge to a point having a potential V. Okay, so now you would have understood that if there is any charge, there will be electric field and there will be a potential due to that charge, right? So if you have to bring a charge closer to that, so that will be Q into V. Okay, Q is the charge being brought. So for example, if we are bringing a charge from, say for example, if this is B, this is A, if you're bringing a charge Q to this place, then what will happen is that, so Q into the potential due to this charge. Imagine if there's another Q here, the potential due to this Q, imagine that if it is V, okay, because this is being brought in an electric field, so the work being done in bringing the charge to a point P, this will be Q into V. Then we have something called a Coulomb's law. Coulomb's law states that the force between two charges, so imagine if there are two charges there, say Q1 and this is Q2, okay, then the force between the two charges, if there are two charges there, so there is certain force there, right? It could be repulsive force, it could be attractive force, right? So this force is given by Q divided by Q into Q1 Q2 divided by R square. Okay, now K is the 1 by 4 pi epsilon 0, right? K is equal to 1 by 4 pi epsilon 0. Okay, and this is normally this is equal to 9 into 10 to the power 9 Newton meter square per coulomb square. Okay, so now if the force is equal to Q1 Q2 R by R square, this is R vector, which signifies that this is a vector. So the electrostatic force on a unit positive charge, then we talked till now between two charges, right? So if it is unit positive charge, this will Q into unit vector R divided by 4 pi epsilon 0 R square. What about the electric field? Electric field is equal to 1 by 4 pi epsilon 0 into Q by R square. Okay, this is the electric field due to a definite charge. So now if I just try to combine this formula, the formula for QR and the formula for electrostatic force, right? So based on the two formula, what we get is that F is equal to Q into E. Okay, so this formula is very important, which we'll be using in our problems. Now we come to something called as a dipole. Okay, what is dipole basically? So dipole, for example, so if there are two charges of the same neutrality, right, or rather opposite neutrality but of the same quantity, right? So this is minus q, this is a plus q. Okay, and they are separated by a definite distance. Imagine that the distance between them is 2a. Okay, so this is called a dipole, right? So for example, this one, say imagine that there are two charges, for example minus q and plus q, and they're separated by a distance, for example 2a, right? It could be any distance for that matter, small distance. So this is called a dipole. Okay, this is called a dipole. So what will be the electric field due to this dipole then? So how will I calculate this? So let's take up two situations, right? One is that we have to calculate P, where P is on the axis, right? So this is a dipole here, and we are trying to calculate on the axis here. Okay, so this EQ, which means that because of Q, what is the electric field here, right? And plus E minus Q is basically because of this minus Q, what is the electric field here, which is 4 pi epsilon Q by 4 pi epsilon 0 1 upon R minus A whole square, right? So this is R minus A. So because this will be A, right? This part will be A. So this distance from here to here will be R minus A, and the distance from this to this will be R plus A. Okay, so that is why 1 by R minus A whole square, and since this is negative charge, so this will be minus R plus A whole square. This is for on the axis. So E becomes Q by 4 pi epsilon 0 4 AR by R. If you just compute this will be, you'll get this one. Now if R is very large, right, if this R distance, that is the distance of P from this dipole, is very large, that is R is very high compared to A. Okay, compared to A, then E is equal to 4QA by 4 pi epsilon 0 into R cubed. Okay, you just compute this here and you should be able to get this. Okay, similarly, if it is on the equatorial plane means it is perpendicular to this, right, and it is here, so P point in this case it is here. Okay, so in this case again the same thing, right? Electric field is equal to EQ plus E minus Q. So now we will compute it in the same manner what we did here, like, right, we have to do the same thing here. For this we'll get a Q by 4 pi epsilon 0, and this is square. Okay, so this will be A, and this is R, so this becomes root of R square plus A square, right? Okay, this also becomes R square plus A square. Okay, root. Okay, so if you just compute in this same fashion what we did here, right? So the electric field at this point P, it will be EQ plus E minus Q. This is equal to minus 2QA upon 4 pi epsilon 0 R square plus A square 3 by 2, and this is P, which is basically signifies a vector quantity, unit vector. Now if R is greater than very large than A, okay, then E is equal to minus 2QA divided by 4 pi epsilon 0 to R cube. Okay. Now if you see both the cases, right, so the dipole moment, we call something called a dipole moment here. Okay, the dipole moment P is equal to Q into 2A, means that what is the value of this, the charge, and the distance between these two charges of opposite nuclearity but same quantity. Okay, so this is called the dipole moment. Dipole moment is equal to Q into 2A, right? This is a formula here. So if we just replace this, so here we got 4QA by 4 pi epsilon 0 R cube. If we replace 2QA by P, so you'll get, in this case, for the axis formula, we'll get E is equal to 2P divided by 4 pi epsilon 0 into R cube. So this is only for when R is greater and very large than A. Similarly, for E on equatorial plane, E is equal to minus P 4 pi epsilon 0 R cube, okay, when R is very high compared to A. Okay, let's go to the next concept now. Let's go to something called a flux, right? So what is flux? Now to learn flux, first let's understand that, imagine that there's a liquid flowing in this pipe. Okay, there's a liquid flowing in this pipe, right? So liquid velocity V, imagine that it's flowing through a pipe of cross section is S, right? So imagine that this cross section of this, right? So there's a cross section here. Okay, the cross section is S here. So flux of liquid across the plane is equal to rate of flow per unit time is equal to V into ds, right? So ds is the cross section, right? Imagine that if this is the pipe here, and if this is the ds, okay, this is ds, okay, right? So similarly for electric field, okay, similarly for electric field, imagine that if you're looking at this particular figure here, when looking at this particular figure here, so if S is inclined, now if this is actually normal, right? So this electric field is normal, or rather this particular cross section is normal to electric field, right? But what happens if it is inclined? So imagine in this case the surface is inclined here, right? Correct, the surface is inclined. If S is inclined at an angle theta to the electric field E, right, here it is E, it is inclined here, then the area perpendicular to the electric field is equal to ds cos theta. Okay, so it will be ds cos theta. So it is like this, right? We need to take the area which is perpendicular to this, right? So we have to take the area which is like this. Okay, so if this is theta, then this becomes ds cos theta, ds cos theta. Okay, in that case electric flux is equal to, so electric flux is denoted by phi is equal to E delta S cos theta. Okay, so the Gauss's law states that the electric flux phi across any closed surface is proportional to the net electric charge Q enclosed by the surface. So okay, so if you look at this particular sphere here, right, imagine if this is a sphere here, imagine if this is a sphere which is enclosing a charge, if it is enclosing a charge Q, okay, enclosing a charge Q, so we'll apply the same formula here. Phi is equal to E into delta S, okay, phi is equal to E into delta S. So delta E we know is Q by 4 pi epsilon 0 R square, and what will be the S here? So S here is here, this we have taken S as only small portion here, right? But for a sphere, what will be the total area here? We know that for a sphere, the surface area is 4 pi r square, okay, where r is the radius of the sphere. Okay, so if we just multiply this, So we should get phi is equal to Q by epsilon 0, okay, where Q is the total charge enclosed by this closed surface and epsilon 0 is the electrical permittivity of the free space. Epsilon 0 is 8.85 into 10 to the minus 12 coulomb square per Newton meter square, okay. So this we need to remember about the Gauss's law and the flux. Let's go to the next concept here, next important concept here, okay. So if there are a system of charges, we saw earlier that the potential is given by, we know that Q by 4 pi epsilon 0 into R, okay. Now imagine that we are in a system where there are multiple charges, then what will be the potential to the system of charges? Again, it is additive in nature. We just need to add them, right? We just need to add them. So this becomes like this, right? Okay. Potential, now also potential energy due to a system of charges is similarly like this, right? Okay. So if there are, if for example, let's take like this, right? If there are three charges like this, so if this is one, if this is Q1, this is Q2, and if this is Q3, okay. So this will be equal to the Q1, Q2, so Q1, Q2, R12, right? If this is 1, this is 2, so this distance, okay, this is R12, this is saying, right? This is R12, okay. Similarly, Q1, Q3, which is Q1, Q3, and this will be R13, okay, plus Q2, Q3, that is Q2, Q3, and the distance is R2, 3, okay. So this will be the potential energy due to the system. Now imagine if it is an octagon, for example, right? If it is octagon, so if it is octagon, what will happen in that case? So similarly, we'll have 8 charges, right? 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8, right? So imagine that each of them had a charge at vertex, right? Q1, Q2, and so on till Q8. So similarly, we have to compute like this, okay? So we'll have to take all the combinations. So we'll have to take Q1, Q2, we have to take Q1, Q3, Q1, Q4, Q1, Q5, Q1, Q6, Q1, Q7, Q1, Q8, okay? Similarly, Q2, Q2, Q3, Q2, Q4, and so on, okay? So we'll have to just add the entire potential energy. This is also called as electrostatic energy, right? And this is equal to the potential energy of a system of charge particles. Okay. Now coming to some specific formula here. If we have a uniformly charged spherical cell, so what do you mean if spherical cell means? We just have a spherical shell, and inside there is nothing, there is no body of the sphere, okay. It is completely hollow. So uniformly charged spherical cell of radius r. So on the surface of cell, it will be, what will be the potential on the surface of the cell, on the surface of the cell, right? On the circumference of the cell, it will be V is equal to Q by 4 pi epsilon 0 r, okay. Inside the cell, electric field will be 0, here, okay. So V is equal to Q by 4 pi epsilon 0 into R, okay. So that will be the formula. So you'll see that on surface of cell and inside the shell, the potential is the same. If you notice this formula, and if you notice this formula, this is same. But what happens if you go outside the cell, right? Imagine if you're taking this point here, then what happens here? So at this point, when R is greater than R, it is V is equal to Q by 4 pi epsilon 0, and R is the distance, right? So wherever it is, right? Imagine this is the distance here, R, okay, from the center, which is O, from the center to this particular point here. Then potential will be V is equal to Q by 4 pi epsilon 0 R, right? Okay. Now, if the sphere was a uniformly charged solid sphere, then what happens? Then below the surface means for any distance from the origin till the circumference, right? So any distance means till here, till here, till here, till here, till here, right? This thing. So at that point, V is equal to KQ by 2RQ into 3r square minus r square. Okay, what is k? K is nothing but k is equal to 1 by 4 pi epsilon 0. Okay, right? So below the surface, right? And so now beyond the surface of spheres, for example, if we are talking of a point which is outside this sphere, then we will have to apply this formula here. B is equal to kq by r. In the same context, we have something called equipotential surface, right? So it is seen here by this time that potential, it depends on the radius, on the distance from the center, right? If it is spherical cell, you have seen that depends, right? So whether you talk of this point or this point or this point, if the radius is r, for example, the potential will be the same. So this is what we call as a equipotential surface. Okay, so equipotential surface, so this will be one equipotential surface. Similarly, this will be another equipotential surface, right? This will be another equipotential, means all these points with this cross have the same potential because they have the same radius, right? So imagine this is a radius r, and if this is a radius, for example, say caps r, for example, right? So all these points, these dots here, they have the same potential, whereas the cross ones have a different potential, but all of them with the cross have the same potential. Okay, so work done in moving a potential positive charge from P to A, PA minus VB is equal to E. So imagine that if the potential on this is V and the potential on this is V plus delta V, so what will be the work done in moving a charge from B to A, right? So if I have to move from here to here, then basically I'm actually moving against this particular charge here, right? So this will be against the electric field. So it means electric intensity, electric field intensity into delta L. Delta L is the distance which I am moving along the radius. Okay, so this is a very important formula. Electric field intensity is equal to minus delta V divided by delta L. Okay, so this is another formula which you need to remember. So these are the key concepts which one should know when we are trying to solve the problems. So now we'll go to the problems. Now I'll try to solve them. So this is the first problem. In this question, it is given that there are 64 drops of same size which are charged at 150 volts each. Okay, so imagine that we have these small drops, right? So each there are drops like this. There are 64 drops here. Okay, there are 64 drops like this, right? Each of them is each is 150 volt. Okay, so now we know that by conservation of charge, like when these drops are joined which have a separate potential, then the charge will be conserved. Okay, so we know that V is equal to K Q by R, right? What is K? K, we know that it is 1 by 4 pi epsilon 0. We know that, right? So let's see the small drop. The potential will be for small drop will K. Imagine that if it is Q, okay, by R, okay, and for the big drop, right, the big one, this is big and I'm saying this is small, this is equal to K capital Q, which is a bigger charge, and R. Okay, R is a bigger drop, so this is the R here, this is the R. Okay, and these are the small radiuses of these small drops. So we need to find out that what is the radius, right, of the bigger one. We do not know the Q also for the bigger one, right? So let's first find what is the radius of the bigger drop, right, which is formed by joining or merging all these small 64 drops. So the volume has to be the same, right? So the volume of a sphere, we know that is given by 4 by 3 pi r cube. Okay, so the volume of the bigger sphere is 4 by 3 pi r cube. This is for the bigger cube, right? Bigger sphere. Okay, and this is equal to 64 times the volume of the small sphere, okay, which is 64 times 64 pi r cube, right? So now 4 by 3 4 pi gets cut here, 4 by 3 pi gets cut here, so it means r cube is equal to 64 r cube, means r is equal to 4r. Okay, so this is a relation. So now what is the bigger one? This is given by k q by r, right? It is k q by r. Okay, so this is equal to k into now q, the since there are 64 drops, so it means it will be 64 into q, right, divided by r. The bigger r, this will be the bigger r, right? So this will be the big r, sorry, this is big R, so this is equal to 4r. Okay, so this gets cut, 16 is equal to 16 into k q by r. So now the 16 to k q by r, this is the voltage of the, or this is the potential of the small drop, right? This is equal to 150 volts. So it means the potential of the big drop, it will be equal to 16 into 150, which is equal to 2400 volt. So this will be the answer. If you look at the options, if you look at the options given to us, it will be the first option. Okay, let's move to the next problem now. In the next problem, it is given to us that in the next problem is given to us that there are 4 point charges, right? So there are 4 point, one is this, then this is the one, this is the second one, third, and this is the fourth, right? They are each at the 4 vertices of the square. Okay, so imagine that, so I have to find that the relation between the potential at the center of the square should be 0. So it means I have to find the potential at the center due to each of these 4 charges. So since this is a square, then each of the diagonals will have to be the same, right? A, imagine that each of these distances from the origin to each of the vertices is A. Okay, so it means that because of this, because of the plus 2q, right, then what will be the potential? Then it will be we know potential, what is the formula? K q by r, we know that, right? So it means k q by r, right? So because of this 2q, it will be k into 2q by a. Okay, similarly, because of this small the 2 and small q, it will be k 2q by a. Okay, because of this minus 3, it will be minus 3q by a, and because of 0.5, it will be, since it's negative, q by a. Okay, so k by a will can take it as cons outside, so it will be 2q. Now this is 2q and this is minus 3q, right? So it will be minus q. and this is plus 2q minus 0.5 small q. This will be plus, okay, so this is equal to, this has to be 0. It says the potential at center of square is 0, so this is 0. It means q minus q plus 1.5 q, this is equal to 0. It implies q is equal to 1.5 q. Okay, so this is the answer. If you look at the options given to us, then this will be the answer. Okay, so friends, we have solved two questions. The video has got a little long, so we will stop the video here now. We will take up the further questions, that is from question number 3 to the future questions. We'll take them up in the next video. Okay, till then we'll request you to please try to solve the other problems and see if you have any clarifications, then please post in the comment section and we will try to help you. Okay, so thanks and see you in the next video. Thank you.